Hi guys, and we're going to be finishing off sulfuric acid because we want to catch up and make sure that we're completely up to date so we finish in our recommended week 9. So we're going to be starting off by talking about the properties of sulfuric acid. Now, luckily we've chosen sulfuric acid and you guys actually know quite a bit about acids. So we've spoken about recently that acids have when they dissociate in water, so H2SO4, when it dissociates in water, it'll have a particular Ka. Okay, now because sulfuric acid's what's called a diprotic acid, which means that it has 2 acidic protons, it has 2 Ka values. With any acid, when the first H is dissociating, we get much more of a sort of complete reaction, if you like, than when the second H is dissociating. So when the second H is dissociating, you might want to represent it with equilibrium arrows. Just give me a second, like this. Now, H3O plus plus SO4 2 minus. Now, basically, I want you guys to be following on with your worksheet because I'm going to get you to be referring to it quite a bit. Okay, so we've got these 2 Ka values. Now, something that I was going to do in class is show you a couple of demos, but I can do that just on video as well. I was going to show you the ionization of H2SO4, which just basically means how much does it get rid of these H's. Okay, now if we have 0.1 m H2SO4, we actually expect a particular pH, because if our concentration of H2SO4 equals 0.1 m, and we know H2SO4 breaks down into 2 H's and 1 SO4, then the mole ratio is 2 to 1. So the concentration of H plus should be 0.2 m, and the pH should be negative log concentration of H plus equals negative log 0.2 equals 0.7. But in actual fact, we get a higher pH than that. We don't get one that suggests that it's only giving 1 H plus away, because negative log 0.1 equals 1. We actually get something between there, something around about 0.8. Now, this gives us evidence to suggest that it is getting, that the H's are at least, H2SO4 at least donates 1 times its H, but donates second H to less extent. Okay, so that's the first thing that we're going to talk about. Basically, this corresponds to this slide, which is talking about sulfuric acid. It is a very strong acid, okay, and it ionizes according to these 2 equations, okay, but it has 2 Ka values. We know that because it is diprotic. And have a look at this. The Ka for the first step is much larger than that of the second ionization. And this is the case with other di and triprotic acids. Okay, so we'll get back to this. Now, this second part is just assumed knowledge from year 11 actually, when it's saying react sulfuric acid with barium chloride. Okay, so that is just simply a double displacement reaction. So I'm going to be assuming knowledge that you know how to write out double displacement reactions and ionic equations, but we will go through it. So double displacement, I guess this is good year 11 revision. Double displacement reactions are those which involve anions swapping cation partners. So A plus B produces B plus CD produces A, and that would go with D plus C, and that would go with B. Okay, so they basically swap partners. Now in this case we have H2SO4. It reacts with barium chloride to produce barium sulfate plus hydrochloric acid. Okay, we know that this is aqueous for sure. Let's just make sure we've balanced properly. We have 2 there, perfect. I'm going to show you what this actually looks like. Okay, so just pop my gloves on. Now we have 1 molar, actually 0.1 molar sulfuric acid. Okay, and we have 0.1 molar barium chloride. Oops. As you can see. Now what I'm going to be doing is simply adding the 2 together, and we'll have a look at the type of reaction. We know it's double displacement, but let's see if we get a precipitation reaction. And put the other one in. And here you can see the formation of a nice cloudy precipitate. Hopefully you can see that. See, you can't really see the green behind it. Okay, so the cloudy precipitate we know is not HCl, so it must be barium sulfate. Barium's one of the things that are in soluble when reacted with a sulfate. Barium chloride is aqueous and sulfuric acid is aqueous. Now, if you remember how to do the ionic equation, if you don't, I'm going to go through it. It only shows the formation of your precipitate. So barium plus sulfate produces barium sulfate. Okay. Now the next thing is action as a strong acid. Okay. So that's one of the properties of sulfuric acid that we're going to talk about. The fact that it is a strong acid. Okay, now we know the 6 different reactions of acids. Okay, I'm going to show you one as an example. So if we have a bit of sulfuric acid inside this beaker, let's pop that in, and we simply add a grain of magnesium ribbon, for example. I will add a couple of pieces. We get this immediate fizzing. Okay, so just bubbling. Now, I do want to use more concentrated sulfuric acid. We'll see how it changes. So I'm going to put the magnesium first, and then I'll put in the sulfuric acid. Quite a bit more violent. You probably can't hear much from where you are, but I can hear it quite a bit. And it's definitely getting rid of the magnesium. So the magnesium used to look like so. nicely in a strip, and now it appears like a bubbling mess. Okay, so it's very much reacting. Now, there are things that you can do to remember these 6 reactions of acids. They don't have to be too tedious. What you do is it's always an acid plus something that it's reacting with. I call this the reacting partner. Now, the only thing you have to do is you look at your acid, and it always gives you the anion. That's all you really have to think about. What's the anion? If it's hydrochloric acid, your anion will be chloride. If it's sulfuric acid, your anion will be sulfate. Then you look at the reacting partner and you ask the following questions. Does it have oxygen? If it does, then you get H2O. If it doesn't, then you get hydrogen gas. Then you ask, does it have carbon? If it does, then you have carbon dioxide. If it doesn't, then you just have water. No, just water. Okay, so let's go through a few examples. For example, we'll actually do it on the back of this. Okay, for example, we have H2SO4, we'll do the full equation, plus, let's do copper oxide. Let's do calcium oxide because I've already closed that. Okay, so you look at your acid. It gives you an anion of the salt. A salt is always produced when an acid reacts. Okay, so importantly, your sulfate will make up your salt, your anion in your salt. And then your cation comes from your reacting partner, calcium sulfate. Plus, we have a look at our reacting partner. Does it have oxygen? Yes, so we get water. Carbon dioxide? No. Calcium sulfate should be aqueous liquid. Alright, so then you can do your balancing, make sure 2 H's here, 2 there, there. Okay, balanced. Then you do ionic. Now ionic, all you have to do are 2 things. 1, separate anion and cation. 2, remove spectators. Oops, spectators. Now spectators are ions which stay in same state. So let's have a go. H2SO4 will be broken up into 2H plus SO4 2 negative. Calcium oxide can't be because it's solid. Calcium 2 plus can be broken up into aqueous, and sulfate plus H2O, which can't be broken up because it's a liquid. Then we cross out the spectators. Now the only thing that's not changing is the sulfate. So our ionic equation becomes, sulfate was actually a spectator in that case. Make sure you've always got your states. Okay, let's do another one. So let's have a look for an example. Add a spatula of, let's have a look, sodium carbonate. So sodium carbonate we've got here inside the beaker. Then sulfuric acid, I'm going to add that to it. We'll see what kind of reaction we get. Fizzing straight away. Sounds like a gas being produced. Let's write out the equation. So, grab this one. So the first thing is the reactants. So H2SO4 again, plus Here it was sodium carbonate. Now, producers. So, let's look. That gives us the anion, so sulfate gives us the anion. Sodium sulfate will be our salt. Then we have to look at the reacting partner. Does it have oxygen? Yes. So we get water. Does it have carbon? Yes. So we get carbon dioxide. So let's write that out. Water plus CO2. Now, let us balance. 2 sodiums there, 2 sodiums there, 2, yep, and 1 carbon there. Yep, that should be balanced. Perfect. Now we have a look at the ionic equation. So this is the full. Ionic only separate the aqueous. So here we go. 2H plus sulfate plus sodium carbonate cannot change because it's solid, produces 2Na plus sulfate plus H2O plus CO2. And again, sulfate is the only spectator. So our ionic equation becomes okay. So let's have a look at the next thing. So those were kind of a revision from year 11. Now, the next thing which I'm going to go through in class again is sulfuric acid's affinity for water. Now, I showed you this example in year 11, but I really want to do it in front of the class again. And it is, if I get a fresh sheet of paper, it is when we get, let's say, a carbohydrate, C6H12O6, and we want to write it in an empirical. Empirical, it would be CH2O. Now, once we remove the water, we can actually turn sugar into pure carbon, which is solid, and water, which actually is gas because it's an exothermic reaction getting rid of this water. Now, the catalyst we use is sulfuric acid. It is what's called a dehydrating agent, and it's very good at dehydrating. Okay, we know this for a fact that it's good at dehydrating because it gets rid of our water in our body, and that's why it can be so bad with burning us. Okay, so I'm going to show you this over here as a dehydrating agent. So this is exactly what we're going to do on Monday, this demo. So sulfuric acid has a remarkable affinity for water, okay? Basically, when it dissolves in water, it releases a lot of heat, which can be really bad because it can boil the water and spit in your face. That's why we never add water to sulfuric acid, and we add small amounts of sulfuric acid to water, because that water that we add will just go straight into a gas and it can get very dangerous. So it has the ability to dehydrate and decompose organic molecules. So I'm going to show you this actually. I'm going to have sulfuric acid. So that's just a little bit of paper towel. I'm just going to add some sulfuric acid to it, see what happens. A very concentrated sulfuric acid, mind you, is what I'm using. Let's have a look. Add a couple of drops. Straight away it goes black. Okay, it's eating away at that. As you can see, it's eating away, it's turning it into a black mess, and that's exactly what it's going to do on Monday when I show you that demo. So we'll let that sit. I'll put it on camera. Okay. So as we said, it's able to dehydrate sugars and remove the carbon from the water. Something else which you guys are very familiar with is if we have, for example, ethanoic acid, and we add that to methanol, what type of reaction am I getting at? That's right, a esterification. So in esterification reactions, we work on, so basically what would be produced here? This is called methyl ethanoate. In esterification reactions, we want to remove water. So esterification reactions are called condensation reactions. And surprise, surprise, we use H2SO4 in its production. Okay, another thing, so I'm going to show you that here. So it can remove waters during the production of esters. Another exciting thing that it can do is if I have a hydrated copper sulfate, for example, it can remove the water from the lattice and turn it into copper sulfate without water. So basically it's really good at removing water. That's why it's called a dehydrating agent. Okay. And this one, we're done with those. Okay, now I guess the sort of final one is action as an oxidizing agent. Now, with these types of questions, I'm going to be just assuming knowledge from chapter 5, which is the redox chapter, and all I want you to be able to do is write half equations and determine oxidation numbers. So for example here we can see that the sulfur goes from 2 minus, that's negative 8, so positive 1, so that's positive 2, so positive 6, so it goes from positive 6 to plus 4, which means that it has been reduced, so it is the oxidant. And surprise, surprise, that it's the sulfur in H2SO4 that is the oxidant, because it's in the same group as oxygen, making it react in similar ways. Oxygen. Okay, so for example here we've got zinc going from 0 to plus 2, meaning it's been oxidized, so zinc in this case is the reductant. Okay, but that's kind of just assuming knowledge from chapter 5. Okay, the final sort of thing we need to go through is the uses of sulfuric acid. Now we've gone through quite a few, but let's just summarize. So we'll skip 1 for now because I'm going to go into that in a bit. But 2, we use it as a strong acid. So, you know, when we want to react it with bases, when we want to react it with the 6 different things that acids react with, when we want to react it, when we want to corrode metals and things like that. We also use it as a dehydrating agent, for example in esterification and things like that, and we use it as an oxidant, acts similar to oxygen. But the first one is in the production of fertilizers. Now, we've got fertilizers here. You don't have to know too much about this, but you have to know that we use sulfuric acid in the production of fertilizers, okay? So basically this has a little bit of nice information. Australian soils are often deficient in phosphorus, which is what we need for plants to grow. And basically in a fertilizer called superphosphate, which is a fertilizer for plants, you can see in this reaction that sulfuric acid is used, reacted with calcium phosphate and water to produce this fertilizer. So it's used in the production of fertilizers. Okay, so last but not least, we are going to go through a couple of things with sulfuric acid manufacturing. Okay, not too many. I just want to go through the waste management and safety. That's all. You're not going to get many questions from me about that. So, waste management, basically, there's a few things in the sulfuric acid process which we spoke about today that can be a problem, but they have thought of good solutions. So one of the problems is actually that sulfur dioxide, if that's emitted, that's actually bad for our atmosphere. It's one of the greenhouse gases, okay? But this process actually uses sulfur dioxide as a reactant, remember, in step 2. So it's really good because we can use byproducts from other industries, such as we said petroleum refineries, so when you have that carbon that has some sulfate embedded in it, and metal smelters, so we said iron sulfide plus oxygen produces SO2, and plus iron by itself. We collect this and use it as a reactant in sulfuric acid production. Then we said also in class the double absorption method. So in step number 2, if it has a low yield, the way we can increase the yield is by passing it through the catalyst many times, the catalyst beds. Okay, another problem is the toxic catalyst. So once the catalyst has been used many times, it becomes spent, is the technical word for it, and basically we need to get rid of it. We dispose of it in landfill sites, so very clean. Anyway, another problem is the heat from the multiple exothermic reactions that are occurring, but actually that's harnessed to generate electricity, and cooling water is usually recycled. Okay, so just have a couple of those up your sleeves, sort of waste management techniques, maybe a multi-choice or something like that on it. Okay, oh, another thing down here, because it has a relatively high boiling temperature, 290 degrees Celsius, you should know why it's so high, because of its bonding. It has a low vapor pressure and there's not much air pollution due to it. Green chemistry. Now, you guys are lucky because I picked the contact process for the manufacturing of sulfuric acid. It was made so long before the idea of green chemistry even came about, but they've actually found that the process is quite green and they haven't made too many amendments to it. Okay, finally is the health and safety. We know that sulfuric acid can be dangerous. We need highly regulated procedures and strict guidelines from when you're dealing with sulfuric acid. Okay, so a number one thing is that it can burn your skin and your eyes, so you just make sure you're wearing correct glasses, face masks, lab coats when you're handling them, and everything like that. Exposure to the H2SO4 mist may cause a buildup of fluids in your lungs, so that's not pretty. If you eat it, it's actually toxic and it irritates your esophagus. Oleum, if you can't remember what oleum was, it was reaction 3A when we produced oleum, when we reacted H2SO4 plus sulfur trioxide, and then we get H2 S2O7, which is oleum. It's that intermediate product. It's highly corrosive and that produces SO3 fumes, so it releases SO3. Basically, you make sure you're minimizing the risk to your workers, making sure that everything's well ventilated so they're not breathing it in too much. Acid spills, basically, we want to neutralize it with a base, but first we put in sand. We cover the spill with sand. Basically, when you react your acid with your base, you might release a lot of heat, and the sand's there to absorb a lot of the heat energy. Okay, now what you need to do in preparation for your SAC, which is coming up in a little while, is doing these questions. Okay, the questions that are in the PowerPoint. Lots and lots of questions. On Monday we're going to spend about a period answering questions, but until then, have a good weekend.